Hi guys. Today we're going to start talking about gases and gas laws. So here we have the kinetic molecular theory, abbreviated KMT. And what this says is that we assume that gases consist of molecules or atoms. So you can think of oxygen, carbon dioxide, helium. These are all things that we associate with as gases. But we can also think as steam, as water in the vapor or gas form. Second bullet here. The particles are so small that their individual volumes are considered insignificant. So gas atoms and molecules that are in the gas form are so small that we feel like they don't even weigh anything. So think about right now, as we're sitting here, we have all sorts of molecules and atoms in the gas form all around us, right? Oxygen, nitrogen, carbon dioxide, even some water, right? Humidity. And we don't even feel that. We don't even think about it. Third bullet, there's a lot of space between gas particles. So gas particles, they're each individual little things and they're moving around. There's a whole lot of space in between them. Gases can be compressed and expanded. So one way we can think of compressed gases is a propane tank that you might see attached to a grill. Hairspray, aerosol sprays, canned air that you can use to clean your keyboard of your computer out. Helium tanks, right, that we can get at like Party City and Party Depot and Walmart and stuff. Those are gases that are compressed into a smaller space. But we can also let gases be expanded and have a whole lot of space in between them, like right now in this room. No attractive or repulsive forces between the particles. So atoms and molecules that are in the gas form don't have those intermolecular forces that we see in liquids and in solids. They're not attracted to each other. They're moving independently. So the analogy that I make for this is like the difference between a group of kids holding hands would be like a solid. A group of kids that are not holding hands but standing together would be like a liquid. And a group of kids that are outside on the playground running around would be like a gas, that they're all just doing their own thing and being independent. Gas particles are in constant random motion. They don't stop moving. They have a lot of energy, the most kinetic energy that an atom or molecule can have. And they are in constant motion, just like those kids on the playground, right? And our last one, all collisions between particles in a gas are perfectly elastic. That means when they do collide into each other, they keep going. They don't stop. All right, so write these down. If you need to pause the video right now, go ahead. All right, so some factors that do affect gas behavior. First off is volume. Whatever you put gas into a volume, if you make the volume very small, we're compressing that gas and it's going to behave differently than if the gas has a whole bunch of room to move around. Temperature. We look at temperature in Kelvin. Kelvin is an absolute temperature scale. We're very familiar with Fahrenheit and Celsius. Kelvin's what scientists use because 0 Kelvin is when molecules have no movement at all. 0 Kelvin actually has not been achieved yet. Scientists are still trying to get to 0 Kelvin, which would mean that an atom or a molecule has no movement at all, no kinetic energy at all. 0 degrees Celsius is equal to 273 Kelvin. So when we want to convert Celsius to Kelvin, all we do is add 273, and then we have the temperature in Kelvin. And so we have to include temperature when talking about gases, because the higher the temperature, the more kinetic energy we're giving a gas molecule or an atom in gas form, and the lower the temperature, then the less kinetic energy that it has. And we'll take a look at that specifically in just a little bit. Next up, we have to think about how much of molecules or atoms are in that container. And remember back to the mole. 1 mole equals 6.02 times 10 to the 23rd atoms or molecules or formula units. Well, when we're talking about a gas that is not, that is at normal STP, standard temperature and pressure, which means 1 atmosphere of pressure. That's what we are at right here, right now, at sea level. Then a gas will be 22.4 liters. 1 mole of gas is neither compressed nor expanded when it fills a 22.4 liter container. We will be revisiting that kind of further along after we learn more about gases. So just kind of keep that in your mind right now, but we're not going to use that right now. And then, of course, pressure. The more pressure you put a gas under, its behavior is going to change. We can all relate to this with those cans that have warnings on them that say contents under pressure. Do not put this near flame or heat. So, we don't want to be throwing that canned air onto the campfire or the grill. That would be really bad, because those contents, that gas inside there, is under pressure. And if we heat it up, it's going to expand and make that container explode. All right, so the last things we're going to look in this video right here is, here we have a cartoon of atoms behaving as a solid. They have very little energy, very little movement. They're very close together, very little space in between them. But then when we go to the next one, here we have a liquid, little bit more space, but at the same time, all the atoms are attached to another atom. They have relationships, intermolecular forces, not as strong as that of a solid. We do have some movement. Atoms or molecules are spinning and rotating around each other. But they still have forces in between them that are keeping them connected. And then here we have a gas. Here we see we have a diatom, probably oxygen, what we're looking at right here. Oxygen is diatomic, wants to hang out with another oxygen. We see a lot of space in between these atoms. And if we look, we see here this kind of blur lines are supposed to show that they have movement. They're in constant movement. They don't have intermolecular forces in between them, no relationship between them. They're just running all over the place, flying around there. Okay, and you heard me reference a couple slides ago about STP, standard temperature and pressure. So standard temperature is 0 degrees Celsius, which if we add 273 to, is also 273 Kelvin. Notice no degree symbol because it's an absolute measurement. And standard pressure is that of what you would find at sea level, which basically we are at sea level here. Standard pressure is 1 atm, and there are different units for pressure. That 1 atmosphere of pressure also equals 760 millimeters of mercury. That's how we measure weather pressure. Like you'll hear the weatherman or woman say the pressure, we have a high pressure system or a low pressure system. They're using millimeters of mercury to measure that. And we will talk more about that later also. We also have 760 torr, which we're not really going to talk about. That's a physics unit. And we also have 101.3 kilopascals, which is also used more in physics than in chemistry, but we will do a couple of problems just so we have that practice. Okay, if there's anything that I talked to through too quickly, please rewind and make sure that you have all these notes, but we're going to pause here for now.